In this video, we're going to go over some other calculations on atomic structure. So we can calculate energy by this equation. Energy is Planck's constant times frequency. So this is nu, it is not V, it is nu. That is representing our frequency. And we know that our frequency is in hertz or in per second. And then our Planck's constant, that is Planck's constant, since it is a constant, it is 6.626 times 10 to the power negative 34 joule second. Now, because Planck's constant is in joule second, multiplied by frequency, which is in per second. So an inverse multiplied by itself cancels out, it gives 1. So our answer will be in joules, and hence our energy is in joules, which we calculate using this formula. So that is how we can calculate the energy of a photon. So whenever an electron is moving from one energy level to the other, we can calculate the energy of the photon if we've been given the frequency of that photon. Now we know that velocity is given by wavelength times frequency. And this frequency, we can also say it's wavelength. We use this symbol for frequency instead of using F. Let's make frequency subject to the formula. So that will be over lambda over lambda. Therefore, our frequency, this is going to cancel out, will be given by velocity over wavelength. So we can substitute where there is velocity frequency there, we put velocity over wavelength. So that is going to give us Planck's constant times velocity over wavelength. Please, this is frequency. This one here is velocity. So we should be able to differentiate those. But remember, in the previous video we talked about something called the wave number. And we say the wave number is a reciprocal of the wavelength. So this equation can actually be written as Planck's constant times velocity times 1 over wavelength. And we know that 1 over wavelength is wave number. So where there's 1 over wavelength, we can put the wave number. So therefore, energy can be calculated also by Planck's constant times velocity times the wave number. So that is how we can find the frequency. So this equation is very important for us to know. We should be able to master also this. At least if you don't want to master, know it. Alright. So there are some other good calculations which we need to understand about when we're talking about this thing. So we need to understand what we call the dual nature of matter. So the dual nature of matter. So this only states that matter can exist both as a particle at the same time and as a wave. So that is what we call dual nature. It can exist in two forms. We know that a wave has some characteristics such as velocity, which is given by wavelength times frequency. So these are the three characteristics of a wave. Every wave should have velocity, wavelength, and frequency. So that is what we have. Now we know that a particle should have mass. So what we are saying is anything that has got mass as a particle. So first, it was understood in classical physics that a particle has no intersection with a wave. Just like an irrational number has got no intersection with a rational number. Now, after some workings by many scientists such as Albert Einstein, de Broglie, and Planck and other scientists, they came to understand that actually a particle and a wave they've got intersections. So that is what now leads to the dual nature of matter. So we have just come to understand that we can calculate the energy of a photon. Remember, a photon is a wave. That is because we know the velocity and also the wavelength. So we can calculate the energy of a photon, which is a wave, by saying Planck's constant times the frequency. Now for particles, Albert Einstein came to say, of course, we know that energy can be related by mass and the speed of light squared. So that is Albert Einstein. And we know that anything that has got mass is a particle. And so we are seeing mass here. Sorry, we are seeing energy there and we are seeing energy there. So de Broglie came to join these two equations and he said, actually, Planck's constant times the speed times frequency, this is frequency, should give us mass times the speed of light squared. So now this one came to say, okay, why don't we say, instead of saying, just saying frequency here, we can say Planck's constant, because we know that frequency is the same as wavelength over velocity, and we actually came to understand that just earlier. I talked about it. So that should give us mass times the speed of light squared. So it is this equation which was further rearranged. Let's try to further rearrange it. We see what is going to give us. So now, instead of saying velocity, we can use a more generalized form, or we can use, let me say, the velocity of light, which is c. So that is going to give us h wavelength over c is equal to mc squared. And I've swapped these two. They are not actually supposed to be like this. Let's get back. We are saying energy is equal to Planck's constant times frequency. And we say that velocity is given by wavelength times frequency. So if you want to get frequency, you divide by wavelength. It is actually the wavelength which was supposed to be down. Therefore, frequency is velocity over wavelength. So that was not the case there. Okay. So we are saying energy by Planck was given by h frequency, and frequency is velocity over wavelength. And then Albert Einstein says energy is mass times the speed of light squared. So we can actually equate this to that to give us hv over lambda is equal to mc squared. Okay, now we can substitute where there's velocity. We can use the velocity of light. That will give us hc over wavelength is equal to mc squared. We can see c there and c there, they can cancel, so we're going to remain with h over lambda is equal to mc. So we can say over 1 and cross multiply. That will give us wavelength times mass times speed of light is equal to h. So let's divide by mc. What we are going to find is that our wavelength is going to be given by h over mc. Now, instead of only using the speed of light, because if we are using the speed of light, we are only talking about a wave. So like the electromagnetic spectrum, they all travel at the speed of light. All those are waves. But we are saying the dual nature of matter says a particle can, a matter can be both a wave and a particle. So we can put V to mean a particle instead of using C, which is talking about a wave. Therefore, this equation now is going to become so now the equation becomes wavelength is equal to h over mv. So this is what we call the de Broglie equation. So that is de Broglie equation. So whenever there's to say calculate the de Broglie wavelength, you want to use this equation where this is Planck's constant and then mass and then velocity. Now from our physics we know that momentum is mass times velocity. Therefore we can calculate wavelength by simply saying Planck's constant over momentum. So that is all the same thing. Alright, so we can be given some different questions on that one, and we can make calculations depending on the question that we're being given. Now let's talk about another concept, which is the photoelectric effect, a very important concept. So what is the photoelectric effect? What does it talk about? So the photoelectric effect is simply a phenomenon which says when light strikes the surface of a metal, electrons are emitted. So this is simply a phenomenon which says whenever light strikes the surface of a metal, electrons are emitted. So if we have got a metal and then light strikes it, so that is light, and we know that the unit for light is the photons which will be coming. Okay, so electrons are going to be emitted from the surface of this metal. So electrons are going to go out. So that is what is known as the photoelectric effect, a phenomenon which states that whenever light strikes the surface of a metal, electrons are emitted from the surface. That is the photoelectric effect. Now this can only happen if the photon or the light that is coming has got a minimum frequency. So it should, the frequency at which this photon is coming should be at least this called minimum frequency, and the minimum frequency is what we call the threshold frequency. Okay, so it's the threshold frequency, and we know that energy is given by hv. So this is, sorry, that is not hv, that is h nu, that is nu, that is the frequency. So energy is given by Planck's constant times the frequency. Now the only way that electrons are going to move out of a metal is if this light which is coming has got a minimum frequency which we call the threshold frequency. Okay, so the threshold frequency is symbolized by nu with a O down. So that is Planck's constant times the threshold frequency is the energy that is required to remove electrons from the surface of a metal. Now if you project light that has got a frequency greater than the threshold frequency, the extra frequency will be used for kinetic energy of these electrons. So that is going to determine how fast the electrons are going to be moving out of the surface of a metal. So now that brings in, we know that kinetic energy is given by half mv squared, where this is the velocity. So now we are saying this is also going to be equal to h. So if you project light which has got a frequency nu, but we know that the threshold frequency is nu o. So if you subtract these two, the extra frequency will be used for kinetic energy. That is how you calculate the kinetic energy of the electrons which will be moving out of the metal. So if you increase the frequency, you increase the kinetic energy of that metal, of the electrons which are coming from the metal. Okay, so if you increase also the intensity of light, electrons are going to be also moving, a lot of them are going to move out. If you increase the intensity of light, the power of light that you are projecting on this metal, more electrons are going to move out of the surface of the metal. So that is how we calculate the electrons which will be released in what we call the photoelectric effect. Maybe we can do some certain questions. We see how we can be able to apply such knowledge. All right, so we assume we project light with a frequency. Okay, let's be kind of scientific. Let's say we project light of a wavelength of 656 nanometers on a metal. So what will be the kinetic energy of the electrons as they move out of the metal? So we have projected, this is light, this is light. So it is light having this wavelength. We project it on a metal. So we are projecting such a light on a metal. Now the first thing is, will electrons be able to move out? So let's have a let's get a threshold frequency. Let's say VO, that is the threshold frequency, is at, let's say, 1.2 times 10 to the power 2 hertz. Okay, so if this is the frequency, will electrons be able to move out? And if they'll be able to move out, what will be their kinetic energy? How fast will they be able to move? So now the first thing is we need to calculate the energy. Okay, so let's first convert this to frequency. We know that velocity is equal to wavelength times frequency. Now because this is light or electromagnetic spectrum waves all travel at the same speed. That is a speed of 3.0 times 10 to the power 8. And then the wavelength is 656. That is in nanometers. Let's convert that to meters by just multiplying by 10 to the power negative 9. And then times that. So to remain with the frequency, we'll simply divide 3.0 times 10 to the power 8 by 656 by 10 to the power 9. Alright. So this will give us, so let's just divide 3 by 656 and then multiply by, we can see that this is 10 to the power 8, this is 10 to the power 9. Same basis dividing, you simply subtract the powers. That will be 8 minus negative 9. Okay, so what we're having is 3 divided by 656. What I'm getting is 0.00457, and then multiply by 10 to the power. This will be 8 plus 9 the power, that will be 10 to the power 17. So multiply by 10 to the power 17. So what I'm getting is 4.57 times 10 to the power 14 hertz. Now as we can see, the frequency is greater than the threshold frequency. So the extra frequency will be used for kinetic energy. So let's calculate the kinetic energy of of how electrons are going to be moving. So the kinetic energy of the electrons. So therefore the kinetic energy will be given by HV. So this is the energy of light which is coming in, minus the energy of light needed to remove an electron from the surface of a metal. That is multiplied by the threshold frequency. So this is energy that is coming in. Remove the energy required to remove the electron from the metal. That will give you the energy needed for kinetic energy of the electron. So we can just simply factorize. That becomes like that. So Planck's constant is 6.626 times 10 to the power negative 34. And then the frequency is 4.57 times 10 to the power 14 minus the threshold frequency, that is 1.2 times 10 to the power 2. So let's start with the brackets there. 4.57 times 10 to the power 14 minus 1.2 times 10 to the power 2. And then we multiply that by 6.626 by 10 to the power negative 34. Okay. So that is going to give us 3.03 times 10 to the power negative 19 joules. So that will be the kinetic energy. We can actually calculate the velocity at which each electron is going to be moving out. So how do we calculate the velocity at which the electron is going to be moving out? One electron is going to move. Okay. So calculating the velocity is not a difficult thing. Of course, we know that kinetic energy is given by half mv squared. Because it is electron which came out, we know the kinetic energy as 3.03 times 10 to the power negative 19 should be equal to half. Now, because we are talking about electrons, we know the speed for electrons. sorry, I mean the mass. We know the mass of an electron. So the mass of an electron is, let me just find out, that should be 9.11. Okay, the mass of an electron is 9.11 times 10 to the power negative 31. That is in kgs. And then times the velocity squared. So we want to determine the velocity. So that is going to give us v squared to be equal to, we multiply this 2 by that, so that will be 2 times 3.03 times 10 to the power negative 19, and then divide that by 9.11 times 10 to the power negative 31, like that. So let's determine now. So we just punch that on our calculators. Alright, so what I'm getting is v squared is equal to 6.65 times 10 to the power 11. We take the square root of that number. So what I'm getting is the velocity is 8.16 times 10 to the power 5. So this is velocity, it's in meters per second. So that is how fast the electrons will be moving out. Each electron will be moving out from the surface of a metal. So fast. So that is a very high speed. Alright, it's a very high speed. Now, having understood this, there's another important concept, which is uncertainty. So when we are talking about uncertainty, we talk about Heisenberg's uncertainty principle. So we are just coming from saying matter can exist both as a particle and a wave. Heisenberg's uncertainty principle. So what does it state? What does it talk about? So Heisenberg's uncertainty principle states that there is a fundamental limitation to just how precisely we can know both the momentum and the position of a particle at a given time. So there is a fundamental limitation. Alright, just a moment. So there is a fundamental limitation to just how precisely we can know both the momentum and the position of a particle at a given time. Okay. Alright. So there is a fundamental limitation to just how precisely we can know both the momentum and position of a particle at a given time. So this is what Heisenberg was trying to say. There is a fundamental limitation to just how precisely we can know both the momentum and the position of a particle at a given time. So what he was just trying to say is, the more you know about the position of something, the less you know about how fast it is moving. And the more you know about the velocity of something, the less you know about its position. So in other words, you cannot fully know the position and the momentum of something at the same time. Having said that, every matter can exist both as a wave and as a particle. If you are talking about a ball, if you push this ball just a little, it will be very difficult for you to tell how it is going to move, like the velocity at which it will be moving. If you just push it just a little so that it just moves like just the slightest inch, it will be very difficult for you to tell the velocity at which it has moved. But you'll be able to tell the position at which it is because you can even see it. But if you are talking about an electron is such a small thing. We cannot see an atom, and an electron is found in an atom. Just imagine how small it is. So we can't tell the position of an electron, but we can precisely say the velocity at which an electron is moving. So we can tell the velocity at which an electron is moving. So the more we know about one quantity, the less we know about the other. That is the uncertainty principle. So Heisenberg's uncertainty principle can be summarized by the equation delta x times delta p is always greater than or equal to h over 4 pi. So the delta x, this is the change in position times change in momentum, will always be greater than or equal to Planck's constant over 4 times pi. So what are we saying? So this value we can see here is a constant. So we can actually calculate, let's try to calculate that one. Planck's constant is 6.626. So that is 6.626 over 4. We know the value for pi. So 6.26 times 10 to the power negative 34. The power negative 34. We are dividing that by 4 pi. So what we are getting is 5.27 times 10 to the power negative 34. So this is a constant. So we always want these two values to give us something that is greater than or equal to this one. So that means for us to get this one, if we have got an equation where we've got xy is equal to 4. If x is 1, then y is supposed to be 4. If x is 2, y is supposed to be 2. If x is 4, y is supposed to be 1. We see that as one value increases, one value reduces. So they are reciprocals of each other. So if we know more about position, we should know less about momentum. If we know more about momentum, we should know less about the position. This is Heisenberg's uncertainty principle. Thank you so much for watching this video. See you in the next video. I'm going to go over some questions on the applications of these principles on the atomic structure.